In this third part of the classes lecture, we're going to look at data encapsulation and information hiding. Encapsulation refers to the bundling of data with the methods that operate on that data. This is what we have done in the previous video, where the data regarding a rectangle, that is its position, width and length, is bundled with methods, such as area. David Parnasse introduced the concept of information hiding in the early 70s. He argued that the primary criteria for system modularization should concern the hiding of critical design decisions. He stressed hiding difficult design decisions or design decisions which are likely to change. Hiding information in that manner isolates clients from requiring intimate knowledge of the design to use a module, and from the effect of changing those decisions. What did David Parnasse mean? A third-party user should know what an object can do, not how it does it. By applying this principle, the implementation itself doesn't matter. When creating a class, what we want to advertise is the object or data structure public interface. In other words, what such object can do. Information hiding increases the level of independence between blocks of code and other classes. We try to avoid as much code coupling with another class. What do we mean by code coupling? We mean that we try to avoid as much as possible having the code of one class A dependent on the implementation of another class B. Class A should interact with class B only via A's public interface. In case the developer of the class B refactors the class B, changing the implementation of one of the methods from the public interface, for example, but not changing the header or signature of that method, our class A will not be affected and will not be broken. We do not need to change our code. Furthermore, let's assume that the developer of the class B uses several attributes in order to make the implementation of the class easier. But these attributes are not part of the API. If my class A uses this attribute directly, and then the developer of the class B refactors the code with a more performant algorithm, and does not need this attribute anymore, they are likely to be removed from the code of the class B. My class A using this attribute directly is broken. It will not run anymore. We have to rewrite the code again. Decoupling the code between classes makes things much easier to maintain because we don't have to look at the dependence upon other objects in order to maintain our classes. Let's look at an example using a class point where all attributes are made public. The attribute X and Y are said to be public. But what do we mean by public? We mean that third-party developers can modify them directly. For example, if we create a point P with a value 1 and 2 for the X and Y, we can directly access the value of X by using P.X, and it returns the value 1. We can also change the value of X by using the assignment operator P.X equal the string 10. Here lies the danger. We can set X to any kind of value, including an invalid value such as a string. So it is essential to protect the integrity of my data structure. We should be hiding the attributes storing the coordinate of my point P. In our current implementation of the class point, there is no information hiding. How can we protect the instance variable as opposed to making them public? In contrast to other languages, such as Java, Python does not have a mechanism that can truly protect instance variables. There is always a way around if we really want to modify an attribute directly. Instead, Python relies on a convention. If an attribute's name is prefixed with an underscore, like _x, the attribute _x should be treated as a non-public part of the API. The same convention applies to method's name. In fact, that will be the responsibility of the user of your API to ensure that they are not going to access such attributes directly or call such a method. Any attributes, function, or methods starting with an underscore should be considered an implementation details and could be subject to change without notice. Similarly, if you are using a class or a module from a third party and you access directly a function, attribute, or method signaled as protected, your code is not protected against an update of this module. Therefore, if the developer of this specific module decides to change or remove such protected attributes, function, or method, that will be your fault if your program doesn't work anymore, not his or her. There are no completely private attributes or methods in Python. That is the most restrictive access to an attribute or method in other languages such as Java. However, for the interested reader or viewer, there is limited support for such a mechanism called name mangling. This is beyond the scope of this course, and we will not be looking into it. Now that we have seen how to create protected attributes, let's refactor the class rectangle seen in the previous video and use information hiding, meaning let's hide the attributes containing the coordinate of the top left corner, the width and the length of a rectangle. First, we prefix all name with an underscore. In addition, to make our code more robust, we should check the input provided in the parameter of the constructor. For simplicity, we assume that the right type of data is provided, in our case, floats. However, we must check that the width and the length are strictly positive. Let's check our implementation and create a rectangle with a negative width. As expected, an error is raised and the program crashes. For the time being, the integrity of our data structure is preserved. Let's assume that the developer using our class really wants to create a rectangle with a negative width and does not follow Python's convention. The developer can do so with a simple assignment. You should note that if the program is not working properly, it is entirely its fault. Having said that, at this stage we should share part of the blame. We provided a data structure where all attributes are protected. If the developer follows Python convention, it should not access any of these attributes, meaning it cannot modify them, but even worse, it cannot read their values either. Once a rectangle is created, the developer is not able to access its width or its length. This class is in fact pretty useless. To improve our implementation, we should provide public methods enabling access to some or all of these attributes. A method that reads the value of an attribute is often referred to as an accessor or a getter. And a method that modifies an attribute is often referred to as a mutator or a setter. For example, we can implement the methods getX, getY, getWidth, and getLength to read the coordinate of the top left corner, the width, and the length of the rectangle. These are pretty straightforward. Now, let's look at the setter. First, we provide the method setX and setY to change the coordinate of the top left corner. More interestingly, let's implement the setter for the length and the width. Within the setters, we must check the input to ensure they are strictly positive. If not, then we should raise a value error. Otherwise, we assign the value to the attribute. Getters and setters are methods and therefore they are invoked the same way as any other method. That is, the name of the object dot the name of the getter or setters followed by the necessary parameters between round brackets. The third-party developer has no excuses for not using the API now. Nonetheless, it decides to have another go at setting a negative width. When executing the program, a value error is raised and the program crashes. This time, the integrity of my data is preserved. To be on the safe side, let's run the program with valid inputs. The program terminates normally, and the output is the one that we expected. How do we decide that a method or an attribute should be protected? This is a design decision. For example, looking more closely at the attribute _x and _y, we can see that the getter and setters are not doing any checking of inputs. In fact, these two attributes should be public. On the other hand, there are restrictions that apply to the width and the length. We made the design decision that we can read and modify them, so we need to provide getters and setters. We can see that the setters need to check the input, and therefore these two attributes should be protected. When designing a class, you need to decide which attributes are implementation details and should not be accessed. Or, if accessed, it should be via getters and/or setters. Which attributes are part of the API and can be public. If in doubt, better make it protected. It could quickly become a bit cumbersome to write all the time getWidth, getLength, and so on, compared to simply using the name of the attribute _L and _W. Thankfully, the Python language provides something interesting called property. Properties use decorator to transform a getter into an attribute. How does it work? Let's look at an example using the getter for the width and the setter for the width. Just before the declaration of the getter, we use a decorator. A decorator starts with the @ symbol, followed by the name of the decorator. In our case, the name of the decorator is @property. Once declared, we define the getter using the keyword def, like any other method, followed by the name we want to assign to the created attribute. In our case, let's call it width. Like for any other method, we need to provide the parameter self. The body of the method is the same as getWidth. From now on, width is an attribute, and we don't need to use the round brackets when invoking it. Let's refactor our code to use the attribute width instead of the getter getWidth and run the code. As you can see, we have been able to read the value stored in the protected attribute _W. We can do the same for the length like so. Now we can read the value in _W. How can we modify it? To define the setter, we use another decorator. The name of the decorator is the name of the property, in our case with .setter. Then we define the method after the decorator. Strangely, the name of the method is exactly the same as the name of the getter. I can hear you say, you are not allowed to do that. We cannot have two functions or methods with the same name. Without going into too much details, the decorator kind of hides the fact that the names are the same. The list of parameters on the body of the method is the same as the setWidth method we declared before. To set the value of the attribute _W, we can use the property width. In addition, the value is changed via the assignment operator like so. Be careful. Width is behaving like an attribute, and therefore you must not add the round brackets. Let's execute the code to see if our code is working properly. Perfect. What about trying to set a negative width? In this case, as expected, a value error is raised. When using a property correctly, the integrity of my data structure is preserved. As you can see, the code is easier to write and also easier to read. Another interesting aspect of the property can be seen when trying to modify the length. We did not provide a setter like we did for the attribute width. Let's try to assign a new value of 5 to the length of the rectangle, p, and then run the program. Look at it. The value 5 is a valid value for length, so there should not be any problem. The program crashes, and an attribute error is raised. We cannot set the attribute length because we did not provide a setter. The attribute length is protected against modification. Changing the length of a rectangle is not part of the API of our class rectangle. It is clear that if we can modify the width of a rectangle, we should be able to modify the length too. We use this example as an illustration of how we can protect some attributes from being modified. Be careful. Do not use property in place of method. They should be used to access the publicly available state of an object. To conclude, before starting the implementation of a class, it is important to define the API of that class. This will guide our implementation. Where property can be used? Which getters and setters should be implemented? Which method and attribute should be public? Which one should be protected? These are the questions we should ask. Now that we have learned about Python classes, we can create the appropriate data structure to solve a given problem. In later videos, we will be exploring linked lists and graphs. These are useful data structures that we can add to our arsenal in order to solve complex problems.